All right, everyone, welcome to the second session on quantum protocols. We're going to have two wonderful talks in this session, but only one speaker. So James, take it away.
Yeah, thanks a lot. Thanks for coming. This first talk will be about cryptography with certified deletion, and it will be joint work with Dakshita Khurana at UIUC. Good, so let's start with the basic scenario of certified deletion. So Alice is sitting on her phone, and she has some data. It could be some images or some notes or whatever that she wants to just like upload to the cloud, so the cloud can store it. And we want this to be private, okay? So, we'll assume that like she's using some encryption scheme and the server can't recover her data from this encoding, okay? But in this scenario, we're gonna want something extra, which is why I'm using like ket notation here to indicate that this encoding is actually gonna be a quantum encoding, because I want to allow for the possibility of Alice later telling the cloud, actually, I would like you to please delete my data. And the cloud, even if they're kind of malicious or like, trying to learn the data or trying to cheat in the protocol, there should be some way for them to perform some like destructive operation on the encoding to produce a certificate that can be verified by Alice that indicates that the data actually was deleted from the cloud's view. Okay, so there's a couple ways you might think to try to at least formalize the security of like what it means for the cloud to actually have deleted the data. So a natural goal would be to say, well, after deletion, we should be convinced that even if Alice's like secret key that she used for this encryption scheme was leaked to the cloud, even then they wouldn't be able to recover the underlying data D, right? Of course, before deletion, if they got the secret key, they could just decrypt the encoding and learn D. So something interesting happened. After deletion, they would not be able to recover D anymore. Another way to formalize this in some cases, which is even stronger, would be to say that, after deletion, maybe we'll just allow the server to have unbounded resources, run at unbounded time. And even then, they won't be able to recover D. So this is kind of saying that D is now kind of information theoretically removed from their view. And so in cases where, like, for example, this encryption scheme, you can kind of, determine what the secret key was given unbounded time. And of course, the second goal strictly generalizes the first. So this is the way, a couple ways to formalize what it means for the data to be deleted. And then also just to check, like, again, like, why am I using both encryption and like quantum information to do this? Well, if the data wasn't encrypted in the first place, the cloud could just recover D, and or in general, D is kind of just some classical data that Alice has. So it's kind of hopeless to obtain any notion of certifiable deletion in this case, because the cloud could just kind of copy D as many times as they want and maybe like pretend to delete one version of it. And that also brings me to unclonability, right? Even this encoding must be kind of have some unclonable properties, because again, like if it was clonable, the cloud could copy it and then pretend to delete one copy. Okay, so we really need both like this encryption and this like these unclonability properties in order to kind of satisfy these goals, right? And there's some prior work on this topic. Most of it, not all, but most of it has been concerned with this first goal, right? And a work that's kind of, inspired a lot of follow-up work in this area was this work of Broadbent and Islam, who basically showed how to construct an encryption scheme with certified deletion, basically for the one-time pad, right? So they construct a single-use information theoretically secure encryption scheme, satisfying this first goal. And of course, in their setting, they're going to allow the adversary to be kind of unbounded throughout the experiment, because the encryption scheme they're using is a one-time pad. Okay. And then there's this really nice follow-up work of Hiroko Morimai, Nishimaki, and Yamakawa that says, look, can we kind of generalize this to much more general settings? Like, can we even use this to construct public key encryption schemes, reusable secret key encryption schemes, even like other stronger forms of encryption, like attribute encryption they talk about. But they also go for this this first goal, right? And in their setting, because they're using some potentially only computationally secure crypto systems, they're going to say that the adversary is kind of polynomial time throughout the experiment. So their polynomial time when they get the encryption, their polynomial time after they produce the deletion certificate, but there they have received the secret key of the scheme. Okay. Good. So now I just want to say what are the three main contributions of our work. So first, we introduced a generic compiler. It's highly inspired by the Broadbent and Islam one-time pad construction, but we kind of use it to give a compiler that should work in many more cryptographic scenarios. Okay, and then probably the main contribution of this work is to kind of improve what we can prove about this scheme, right? So we kind of develop a new proof technique that allows us to show that this compiler is secure in many different scenarios, and also satisfies the second goal that I had on the last slide, which shows kind of an everlasting security guarantee, where the data is actually information theoretically removed from the adversary's view after deletion. Okay. And something I'll talk about at the end of the talk is we also consider certified deletion in a two or a multi-party crypto context. And in this context, we introduced a notion that we call everlasting security transfer, which again I'll explain a little bit later. So let me start by describing the compiler. So let's take ENC to be any semantically secure crypto system. You could think about it as a public encryption scheme, or even just kind of a computationally hiding commitment, or FHE, whatever you want. Now, if I want to use that and kind of augment it with some certifiable deletion property, what I can do is I'll sample basically lambda Wisner encodings, or BB84 states, whatever you want to call them. So they're described by a X and theta, which is your choice of bases. And just for notation throughout this talk, I'll let T refer to the indices where, I guess that should say where theta I is equal to 0. So these are the indices where X is encoded in the computational basis. And so the ciphertext is just going to consist of the lambda BB84 states. It will consist of an encryption of the bases theta. And then we're going to take the B that we actually want to encrypt and mask it with all of the XIs that were encoded in the standard basis. Okay, so this will be the ciphertext. And then we need to specify some verification key that will be used to verify the deletion certificate. That will consist of theta and the X's that were encoded in the Hadamard basis. Okay, so I guess before I get to deletion, maybe we can just verify that if we're given, this should be a correct scheme, right? So if we're given the decryption key for this encryption scheme, we should be able to recover B. Well, if we are given that key and we can recover what theta is, then we know which of these states to measure in the standard basis to learn the appropriate XIs. Okay, and then we can use those XIs to unmask B and learn B. So decryption is fairly straightforward. For deletion, the intuition is that, well, we're using all of the X's that are encoded in the standard basis to mask B, right? So we want to have a deletion procedure that forces the adversary to kind of remove those X's from their view. So what we'll do is we'll just ask the adversary to measure all of these states in the Hadamard basis, right? So that's kind of the honest deletion procedure. If they do that, they'll get some set of bits, X prime. And to verify that they did that honestly, or almost honestly, right, we can basically check, given the verification key, that X prime matches X in the Hadamard basis positions, right? So the intuition is that if they have produced an X prime that matches all of these in the Hadamard basis positions, then they must have basically measured everything in the Hadamard basis, thus destroying the information about the X's that were encoded in the standard basis. Okay. So this is the compiler. Now, let me describe what we actually want to prove about it, right? So I'll define this experiment, this certified deletion experiment, which is parameterized by the encryption scheme and by some adversary. And basically, we're just going to give the adversary the ciphertext. So it's also parameterized by some bit B. We're going to encrypt B, give the adversary the ciphertext, and then we'll let them output a deletion certificate, X prime, along with some whatever leftover state they want. So I'm going to call a row like the leftover state of the adversary. And now I'm interested in the case where they actually produce a valid deletion certificate. So I'm just going to kind of abort the experiment if it's invalid. And the goal here, right, is to show that, whether or not I originally gave the adversary an encryption of the bit B or an encryption of the bit B, or the bit B equals 0 or an encryption of the bit B equals 1, their final state, conditioned on successfully deleting, should have negligible trace distance, right? So this really captures the fact that there's statistically no information about B left in their state if they have passed deletion. Okay, good. Now, the intuition again, right, is that, why should this be true? Well, if the adversary doesn't know what theta is, in order for them to pass deletion, they pretty much, intuitively, they need to kind of just measure all their states in the Hadamard basis because they don't know which ones are going to be checked by the verification procedure, okay? And that would establish that kind of these xi's for I and t are kind of gone. The tricky part of getting formalizing this intuition is that, well, the bases theta are actually given to the adversary, of course, in encrypted form. Okay, so somehow we need to kind of remove it seems like we kind of need to remove this information from the adversary's view in order to kind of argue that what they must do to produce the deletion certificate is measure everything in the Hadamard basis. And the prior work that I mentioned basically, follows this very natural approach. They basically just define a hybrid where we have removed the information about the bases theta from the adversary's view. And in order to do that, they assume some extra property of this encryption scheme, which is a non-committing scheme, which I won't get into the details of. But I think that there are a couple drawbacks of this approach. The first is it compromises generality. Ideally, we would like to just use any semantically secure encryption scheme. We don't want to have to assume it satisfies this extra non-committing property. As a particular example of this, we don't know any FHE schemes that are also non-committing. So if we want to kind of generalize this to more advanced primitives, it would be nice to get rid of this requirement. And it also, when we move from a hybrid from an encryption of theta to an encryption of 0, that's like a computational hybrid switch. So that's not going to suffice to prove this claim at the bottom, right? It's not going to suffice to prove everlasting security. We want to come up with kind of a hybrid argument where all the hybrid switches are statistical, because actually what we're proving is a statistical claim. So, basically what we do is we get around this by, we don't define a hybrid where we remove theta, okay? Instead, we kind of directly show that the adversary's strategy, in order to produce a valid deletion certificate, must be actually close to the honest strategy of measuring all of the states in a Hadamard basis. And we basically use the computational security of ENC to show that some predicate on the adversaries and challengers system must hold. And given that the predicate holds, this claim must be true. Okay. And so I'll spare you the actual hybrid argument. It's actually not that long, but I'll encourage you to see the paper if you want to see actually how we turn this intuition into a proof. Okay. All right, good. So now let me just go through basically the results that we get. So we can instantiate ENC with a bunch of different encryption schemes and kind of improve prior work in this area. So basically, we can say, we'll just automatically get a public key encryption scheme with certified deletion, even a fully homomorphic encryption scheme, and then even some of these other primitives at the bottom, like commitments and zero knowledge proofs. And in many cases, we kind of improve prior work in the sense that we go from this weaker definition, this key leakage definition, to this everlasting security definition. In other cases, for example, in fully homomorphic encryption, we have basically the first FHE scheme with certified deletion from standard assumptions. This prior work did had a conjectured scheme, and if you were here Monday, you saw that scheme actually gives an alternative approach to getting FHE with certified deletion from standard assumptions, which we were able to prove in this follow-up work, which was presented on Monday. And then, some of these other primitives used random oracles, and we can just do them kind of in the plain model, just all based on our compiler. Okay. Good. So I think I would now like to move on to the setting of two-party cryptography. So basically, what we've been talking about is a setting where we have Alice, we kind of have like one honest user, and she's just kind of encrypting her data and sending it out to the world, and the world is the adversary, right? So now, in the setting of two-party cryptography, we have kind of like two parties that are mutually distrustful. They might each have a private input. They want to compute some function of that private input. And we want to allow for the possibility of either party being adversarial, okay? And so the question that we can ask is, can quantum information actually provide any useful notion of deletion or everlasting security against both or either party in this kind of more demanding setting, right? So there's some prior work in this area, at least kind of implicitly starting to address this question. One of the most fundamental results in quantum crypto is this Myers-Low-Chow impossibility, which says that, okay, well, at least the best that we can hope for in this setting is impossible, which is to get unconditional security against both parties. And so they show this for the case of bit commitments, which can kind of be seen as like maybe the simplest form of two-party crypto. Okay. All right, fine. Unruh actually showed many years later, well, he considered like a natural follow-up question, which would be like, well, what if we assume that the adversaries are computationally bounded during the protocol? Can we still hope to get some notion of everlasting security after the protocol against all parties? And he showed that this is also impossible by extending this Myers-Low-Chow impossibility. Okay, so it's pretty much established that we can't do everlasting security against all parties. Now it's useful to check, well, in the classical setting, what's the best that we can hope for? Well, we can achieve unconditional security against some fixed subset of parties. Again, imagine like a commitment that can either be statistically binding or statistically hiding a zero knowledge protocol that can either be a proof or statistically zero knowledge and so on. So the question remains, is there any way for like quantum information to basically improve on what we can do classically in this setting? And we show that there is kind of this in-between notion that is impossible classically and becomes possible with quantum information. We call this everlasting security transfer. And the basic idea is that after the parties run the protocol, and we're going to say, maybe they're computationally bounded during it, what we can achieve is that, for example, party one can say after the protocol, actually, can you please delete my data? And party two should be able to produce a certificate that establishes that all information about X1 that they previously maybe had some computational information about has been statistically removed from their view. And of course, we want to maintain some security against P1 as well, or against P2, okay? So, but we can also say, actually, maybe it was P2 that wanted to request that P1 deleted the data, okay? And we kind of get the opposite guarantees, okay? So the basic idea here is that we want to allow for the possibility of, after the protocol, either party can request deletion, even if the protocol was previously statistically secure against them. Okay, so that's where this name of transfer comes from, right? And so it gives like this kind of like dynamic statistical guarantee where you don't really need to know before the protocol starts like who you're going to want to get statistical security against. And I will mention this generalizes some previous notions that appeared in the literature, such as like a statistically binding commitment with certified everlasting hiding also gives this kind of transfer ability, okay? And now I do, just to maybe motivate this notion a little bit more, one nice like toy application you can imagine is like, say you want to use MPC to run an election, okay? So these parties are gonna all tally up their votes and elect two of them, let's say like P2 and P3 to be president and vice president. So now, what would everlasting security transfer allow us to do? Well, it would allow like the citizens to request that the elected parties delete their votes, okay? And give the guarantee that after the protocol completes, these elected parties have like statistically no information about who like did or didn't vote for them. And so the idea here is like we would need everlasting security transfer to do that because we don't know beforehand like what the result of the protocol was. Like we don't know beforehand who we actually would want like the stronger statistical security against. All right, so this is the notion. Now let me quickly say what actually results we get about this notion. So we start with like standard statistically binding computationally hiding commitments, okay? And what we do is we can use a couple invocations of our compiler plus some ideas from this prior work to build what we call ideal commitments with everlasting security transfer. So these are commitments that satisfy this like ideal commitment functionality. And then once we have that, we prove this like sequential composition theorem for protocols with everlasting security transfer, which allows us to rely on prior work that shows how to take ideal commitments plus quantum communication, build OT, and then build MPC from that. So kind of from the end of all of this, if we just start with this really basic cryptographic assumption of statistically binding computationally hiding commitments, we can go all the way to this general setting of MPC with this notion of everlasting security transfer. Okay, and I think that's all I wanted to say. So happy to take questions on this.
So we have time for one or two questions.
So what frame, can you hear me? Yeah. What framework do you use for the composition results? Is it Windows or?
What framework? I guess we define our own, like we do sequential composition. So are you asking about whether we do like UC or? Yeah, we don't do UC. Yeah, just sequential composition. Yeah. Mm-hmm.
Yeah, James, very nice talk. Just it seems like you kind of solve everything. Like, is that the like are there still like open questions now and everlasting security, or does this kind of like handle all the interesting primitives?
Yeah, there's even been more follow-ups even since this work. For example, like you might want to ask for like publicly verifiable deletion, which we don't have in this work. You might want to, and so one thing I didn't get into also was like we can do FHE with certified deletion, but like one thing you might want to turn this into like a full-fledged like delegation protocol with like malicious security guarantees, and like we don't handle that in this work either. So there are certainly some things that were left open. I think there still are some interesting things open as well.
Yeah, got it. Thanks. So like, I guess when it comes to just these guarantees that you talked about today, though, like certified deletion with like private verification and everlasting security, like it seems like, is it right to understand like all the major primitives have been handled though, where it's possible to ask for this?
Yeah, I don't want to say like all the major primitives. Like
Sure.
there's yeah, but a good number of them. Yeah.
Great. All right. Thank you. I'll thank the speaker again. So we'll have our next talk in about 2 or 3 minutes. It'll be James again.
Unclear. That's a good interpretation.
Right, so if you're just joining us, we have James Bartuszak again, who is going to tell us about zero-knowledge teleportation. Okay, take it away.
Oh, cool. Yeah. All right. Thanks for staying. So this is right, secure computation with shared EPR pairs, joint work again with Dakshita Khurana, and also with Aksharam Srinivasan. Okay. So suppose Alice and Bob are playing a card game, and Alice has 2 cards, and for some reason she's supposed to let Bob learn one of them. Okay. Without knowing which one that Bob learns. Okay, good. So, you could, during the course of playing this game, you could wonder if Alice could kind of just look at her cards, kind of like write down a message, send it over to Bob, and allowing him to learn exactly one of these 2 cards. Now, it's pretty clear if you think about this for a little bit that this is just completely impossible, right? I mean, Alice could just kind of write down her message, and then right before she sends it to Bob, she could just pretend to be Bob and see which card that he learns, right? And so the main result of this work is to show that this becomes possible if it was the case that Alice and Bob had some pre-shared entanglement in the form of just shared EPR pairs, okay? So kind of the simplest form of entanglement, if they're kind of, if they had this setup, then indeed Alice can, look at her cards, look at her halves of EPR pairs, write down a message, send it to Bob, and satisfy these requirements. So of course I'm talking about oblivious transfer. And in words, our first result here is that assuming the sub-exponential hardness of the LWE problem, there exists a one message random receiver bit string OT protocol in the shared EPR pairs model. So it's a lot of words, but again, just to have the visual here, we're going to be clear about the model, we're going to assume that there's, you could think about it as some trusted dealer, some trusted setup that just prepares, deterministically some shared EPR pairs, sends one half of them to Alice, the other half to Bob. And now we want to realize this ideal functionality, which just takes 2 strings from Alice, samples a random bit B, delivers MB to Bob, and we want to realize it in just one message. Okay, so Alice sends a single message to Bob. Okay. Now, just to put this result in context, the most relevant prior work here is earlier this year, we gave a protocol in this setting with a couple maybe different properties. First of all, we needed a random oracle. But worse, the protocol that we had earlier only worked for bit OT, okay? Which is where Alice's input messages are only single bits. Now you might be thinking, well, we know bit OT is kind of complete for everything, but not in the non-interactive setting, okay? In the non-interactive setting, it's not known that you can just go from bit OT to string OT like this. So we needed to design a different protocol to get string OT. And moreover, like string OT is really the thing that becomes useful, okay? As we can show via these corollaries. So first of all, relying on this work of Garg et al. From a few years ago, once we have a one message non-interactive string OT protocol, we can use that to obtain a secure computation protocol for any unidirectional classical functionality. So now these parties are going to realize an ideal functionality that takes an input X from Alice, potentially samples some random coins if it's a randomized functionality, and delivers the output to Bob. Okay. And I do also want to mention some related work about non-interactive protocols. This GIKOS work, along with some follow-ups by now, they study these type of protocols in a different model, which is kind of the noisy channel model. And so here, Alice and Bob are separated by a noisy channel, which is provably going to kind of drop some random bits along the way. And they study the possibility and impossibilities of one message protocols in this model. And I won't kind of state what their results are. But I will say that basically we study a very similar question in a different and incomparable model, which is this kind of shared EPR pair model. Okay. Good. So now we're in the quantum setting, so we can even go further, right? Implicit in this work from a couple of years ago, we can show that once we have a unidirectional or a protocol for any unidirectional classical functionality, we can boost it to computing any unidirectional quantum functionality. So now here the ideal functionality is defined by some public quantum map Q. it takes as input, some state row from Alice and delivers to Bob Q of row. And again, we can do this in the shared EPR pairs model just with one message of communication. And you might be thinking that this setting is actually quite similar to the setting of quantum teleportation, right? And we call this a secure teleportation through the map Q. Okay, so why is that? Well, again, in teleportation, we have Alice and Bob. They share APR pairs. Alice sends a single classical message to Bob and transmit a state row to Bob. And so here we can say that under cryptographic assumptions, Alice can again send a single classical message to Bob, now with the guarantee that she's transmitting her state like through some map Q, right? So so Bob is guaranteed that the state that he gets has gone through this map Q. Alice kind of learns nothing about any of the side information that was computed while preparing Q of row and so on. So you can kind of think about this as teleportation, but it's like the state is going through this map Q on the way. And there's some special cases of this notion. So for example, this would give a NIZK for QMA, again, in the shared EPR pairs model by just taking Q to be a QMA verification circuit and rho to be the witness. And actually, there is a prior work that studies, of this work of Morame and Yamakawa, studies NIZK for QMA in this model. And they gave a protocol in the random oracle model. We give a protocol in the plane model, but from sub-exponential LWE. And then also in the paper, we can go beyond QMA and consider even like state synthesis tasks. And we formalize what we mean by this zero knowledge state synthesis. And we show we can do this again in this kind of non-attractive setting. So for details of that, you should see the paper. OK, so this is all I want to say so far about at least our results in the one message setting. We also studied the shared EPR pairs model in a multi-party setting, right? So here we can imagine multiple parties all start with some shared EPR pairs between each pair. And we want to study this primitive of MPC, right? So where every party now has their own private input and they want to compute some function on these inputs. And what we can show is there exists in this model a two-round and a round optimal in this setting protocol just from the black box use of hash functions, okay? And there's two relevant lines of research to put this into context. The first would be that, if we're okay assuming, let me say, like structured assumptions or like assumptions that are used to build public key crypto, then there's a long line of work that culminated in showing that we can do round optimal, two-round MPC, even in this weaker setup model, of course, this just CRS model, okay? And then on the other hand, if we don't want to use structured assumptions and we're okay with quantum communication, there's again a very long line of work that culminated in showing that we can achieve multi-round MPC without structured assumptions. Okay, so in our work we basically show that in the shared EPR pairs model you can kind of get the best of both worlds. You can get round optimality, two rounds, and without using structured assumptions, we just need to use hash functions. Okay. All right. So now I will spend kind of like most of the rest of my time talking about the one message protocol. So in particular, our one message OT protocol. Okay. And it basically suffices to come up with like what I'll say are OT correlations, which are just kind of two random strings that Alice receives and a random bit B along with RB that Bob receives. And once they have this, Alice can just use her two strings to mask her chosen inputs, right? And so we're going to generate these correlations in three main steps, okay? So first, we're going to use the shared EPR pairs to generate some insecure correlations. So they look like OT correlations, but they're not quite secure. We'll kind of identify the source of insecurity of these correlations and basically run what can be seen as like a deletion protocol on top of it to turn these insecure correlations into weakly secure correlations. And finally, we'll combine these weakly secure correlations into one strong OT correlation, which can be used to get our protocol. Okay. So let's go through how we do this. All right. So for the generate step, let's suppose the sender and receiver start with n+1 shared EPR pairs. So each of these like squiggly lines is just one EPR pair. And I'm going to label the first pair as like the control qubits, and the next n as the message qubits. Okay. So now I can write shared EPR pairs, like n+1 shared EPR pairs is basically just a uniform superposition over all n+1 bit strings copied, right? So I'm going to call like the left copy like the sender control sender message register, and the right copy the R control R message register. And the basic idea is quite simple. So the sender, she will just sample a random n-bit string x, and she'll basically apply this controlled like XOR with X operation from her control register to her message register. And so what that does is basically XORs X into her message register, conditioned on the control register being 1. And now just by change of variables or symmetry, like this state, I can just write the state identically like this. And this is useful because now if we have the sender just measure her control register after performing this, or measure her message register after performing this operation, the joint system basically collapses to just a superposition over 2 different strings, right? So on the receiver's side, they either have V or they have V XOR X. And the sender knows what both of these strings are, right? She measured V and she chose X at random. So kind of these are the 2 kind of sender OT correlations. Of course, if the receiver just like measures his half of these EPR pairs, he's going to get B, and he's going to get one of these 2 strings, V XOR B times X. Okay. So this is great. This just looks like a nice string OT correlation, right? So why is this insecure? Well, the sender has, still has this control register around, and if she just like measures that control register on the standard basis, she will learn the bit B that the receiver has, right? So this just exactly leaks the receiver's choice bit B to the sender if the sender does this, okay? So our idea is going to basically be to request that the sender doesn't do this by instead asking them to delete their knowledge of B by measuring their control register in the Hadamard basis, okay? And if they comply with this request, if they actually do this, then we can write the joint state of the system like this. So if they actually just take their controller register and measure it in the Hadamard basis, on their side, their information is just H and V. And the receiver still has like the superposition over either 0V or 1 VX or X, kind of with a random phase that they don't know about, okay? So of course, we don't want to trust that the sender is always going to just be doing this measurement for us. Like, of course, in fact, even a semi-honest sender might just kind of look at the register first. We can't really prevent that. So, one way that we can come up with for having the receiver check that the sender was actually doing this measurement honestly is just to say, well, if the sender just sends over all the information they gathered from doing this, which is like V, X, and H, the receiver can actually, project their halves of these EPR pairs onto what the honest state should be, which is written here, okay? And if the projection accepts, then they can be fairly convinced that the sender was indeed being honest. So, of course, if the sender sends over all this information, there's no useful secure correlations they can get out of this. So we're basically in a situation where either they can kind of measure correlations, or we can have the receiver check that the sender is being honest. So this suggests like a natural cut and choose approach, where we repeat this protocol, this basic protocol, a bunch of times. And we kind of choose some of them to check, and then choose the other set to measure to obtain correlations from, okay? So we can do that as follows. We will have the sender commit to all of their information they get from these L repetitions, okay? And we want to pick some random subset of these commitments to open to the receiver so he can check, okay? And we want to maintain, we want to keep we want to stay in this non-interactive setting, so we'll use Fiat Shamir for this. So let's say we have some hash function that the sender applies to this description of their commitments in order to sample this random check set T, and the sender will transmit the opening keys for this set T. And like I said, for this set in T, the receiver can project onto the honest states and kind of abort if any of them fail. And if they all accept, then we'll just take the unchecked sets, so for I not in T, and the parties will just kind of measure them, as I described in the earlier slide, to get some set of correlations. Okay. So now, what can we prove about these correlations? Again, it's not like they're all going to be perfectly secure, there might actually be some BIs here that the sender actually knows. Maybe the sender was dishonest in like a couple of these positions and wasn't caught, and like they kind of completely know some of these BIs. So really the main, like the heart of the security proof is this claim, which is we managed to show that assuming this hash function is sub-exponentially correlation intractable. I won't really define correlation intractability, but we can show that actually these BIs aren't all random, but if we XOR them all together, that resulting bit is actually uniformly random and independent of the sender's view, no matter kind of how malicious they're being, if the receiver didn't abort, right? Okay, so this kind of defines what I mean by these weakly secure correlations. So they have some set of correlations that are weakly secure in the sense that like if we XOR all the receiver's choice bits, then that's actually a kind of a secure choice bit, okay? So the last step is to combine these. And actually at this point, this is kind of just like a classical question. We have the sender with like, let's say k, sender and receiver with like k different weakly secure correlations that satisfy this guarantee. And the easiest thing that you can imagine doing is kind of just like XORing all the receiver's correlations together. This doesn't work because that gives kind of 1 out of 2 to the n possible strings that the sender could have transmitted. And so we want to take this and reduce it to a case where there's really just 2 strings for the sender to transmit. Here, we can basically do this pretty indirectly using some ideas, for example, from like free XOR. So basically, the sender will sample some fresh strings, okay? XOR them all together. Well, I'm going to call T to be the XOR of all these strings, and then the sender will just sample a single offset delta. And the sender will transmit commitments to all of these strings and their offsets, where we set the commitment key to be these RIB correlations that they previously had, right? So what this means is that basically the receiver can learn 1 out of 2 of each of these underlying strings, depending on which RIB they had. And basically, what this gives us is a way to say that, well, the sender's 2 strings are T XOR this offset, and the receiver will get 1 of these 2 strings, and which they get exactly just depends on the XOR of all their bits BI. Okay, so maybe this was a bit quick, but this is kind of just a classical question, and you can kind of see the paper for the details about how this works. Okay, so good. That's the overview of how we get this one message protocol to work. Before I end, I just want to say have one slide about our 2-round MPC protocol, right? So the goal here is to get 2-round MPC, again, from the black box use of a hash function. And our approach is to obtain what we call a black box friendly OT in the shared APR pairs model. And then if you're familiar with this Garg Srinivasan compiler, we're going to apply it to the OT to turn it into a 2-round MPC. And our OT roughly looks like this. It operates basically in 2 phases. So in the first phase, Alice and Bob each kind of measure their qubits, and then you make use of a hash function and some cryptographic operations. Alice sends a message to Bob. Okay. Now in the second phase, this is an input-dependent phase. So there's a message that depends on Alice's bit, and then a second message that depends on Bob's input. But the nice thing about this phase is it's completely classical and it's completely information theoretic. So the first phase we're going to perform, because it's kind of like quantum and non-black and uses crypto, we're going to perform this outside of the GS compiler. We're going to perform this information theoretic part inside the GS compiler. Okay, so that was a quick overview. I will say that the OT that we use to build this is actually builds on pretty directly on this prior work that I mentioned. And if you're wondering what I mean by black box use of a hash function, how do we formalize security, we can argue security either in the quantum random oracle model, or we can even say specifically from extractable commitments and correlation intractability. Okay. All right, so let me just conclude. So basically we study this shared EPR pairs model where we assume there's a trusted dealer that distributes shared EPR pairs. And I think it's an interesting model for a couple of reasons. For one, it seems fairly natural actually, given the way that quantum internet proposals are today, which is basically to exactly just like set up shared entanglement among a bunch of different nodes, right? And the reason it looks like that is because of teleportation. Like once you have shared entanglement, you can communicate quantumly however you want. So I think the nice thing about this work is like we're taking some form of setup that's already been shown to be very useful for other reasons and showing that we can do some useful cryptographic things with it that aren't known or are impossible classically. For example, one message secure computation protocols and round optimal MPC without structured assumptions. Okay. And then I do want to mention there's a really nice concurrent work that of Collison, Muguruza, and Spielman that studies a bit of a different question, which is, can we construct just a 2-message OT, again, without public key assumptions, but in the CRS model? And so they managed to construct this. And what both their work and our work actually leaves open is, can we take either their protocol or our protocol or a different protocol, improve it in some way, and obtain a 2-round MPC in the CRS model? So we need to use shared APR pairs, but there's no reason to think that we can't get away with just using a CRS model and try to get 2-round MPC from hash functions. So I'll just leave that as an example of a potentially interesting open question to think about. So yeah, thanks for listening again.
Thanks, James, for the great talk. I think we have time for maybe a couple questions.
Hey, thanks, James. Can you go back to the sort of protocol, to the template? So what is actually Bob doing? So he gets a message and then
Maybe,
yeah, further back.
maybe here?
Yeah, right.
Yeah, so, okay, sure. So he gets this message. He opens some of these commitments.
Right. But
And
he always, so for the yellow part, he's always just measuring it, right? Like,
so for the check positions in T, he performs like a different measurement, which was kind of like on this slide. In the honest case, those registers look like that on the R side, right? So he's actually going to perform a projection onto that state to check that Alice is being honest. So, for some of these positions, he receives V, X, and H, so he knows what projector to like apply. Okay. So
I see.
yeah. And then for like the I not in T, he just
Then
does
you
the
just measure it in
measurement
computational
to
basis.
get the
Okay.
correlations.
So you do need to do it in more than one basis.
Yeah.
Thanks.
Maybe one more question if anyone has one. Maybe I'll ask a question. James, if you could go back actually all the way to your slide where you showed the desired functionality for like where Alice sends a state rho and it goes through some process queue.
Yeah.
I guess I was wondering, or this made me think about the connections to deletion, since that's on my mind. Is it valid to think of this as like, I mean, you're saying Q, you can think of it as purifying Q. It's like some circuit on some ancilla registers as well. And is the goal really that like you want some protocol where like some qubits of the resulting like purified circuit are just deleted from the point of view of Alice and Bob?
Yeah. So this is again, like you're saying, like Q could be some arbitrary CP/TP map, right? So there is maybe some side registers produced, while computing Q that are just kind of gone. Like neither Alice nor Bob learns what's in those registers.
So is there some hope of like, saying that these kinds of protocols, or maybe the underlying OT, are those like particular instances of like deletion primitives, or is it like not quite so clear cut?
Yeah, I'm not sure. I mean, I see what you're saying, that there's like, the way that we actually go from classical to quantum here is like using these like quantum garbled circuits, right? And so like there is some notion of just kind of like, there's some measurements that are happening that like are kind of encrypted and no one knows what they were. So like actually you can consider those to be deleted, but they were kind of never known either. So yeah.
Thank you.
Yeah.
All right, let's thank the speaker again. Yeah, you turn it on, turn it off.